you have you been able to upload?
Okay, the motor effect. We're going to start with looking at what to start with page 1 on your course notebook. And we're going to look at, because the new topic is motors and generators, the first thing we're going to look at is motors. What is the basic principle behind all motors? And the motor is different than an engine. So you have an engine in a car, and that runs on petrol, or diesel, or gas, and it has combustion in it. So we burn petrol, create movement. We are not talking about this. This is a motor. A motor is an electrical device. So we use electricity to somehow create motion. And the word motor itself comes from a Latin root, moto, which means movement. Okay. So the motor effect we're about to look at, we're going to do a small demonstration in a few more moments, is how to use electricity to create motion. Okay. So, moving on. The principle behind creating motion with electricity is that charged particles, and for us, for our understanding at the moment, it is the electron. Charged particles, when they move in the presence of magnetism or a magnetic field, they get pushed and pulled and they experience force. So here is the opening line of, it says complete this paragraph in your book. It says a charged particle in the presence of a magnetic field would experience a force. That's just meant to be a force, that's not meant to be anything there. So cross that out. Oops, can't do that. And this force acts at right angles to its direction of motion. So here I've got a charged particle and it's moving this direction. So if it's moving that direction, it gets pushed at a right angle towards its direction. Okay. Now we have met this type of motion before. If I move in one direction, say this way, and I get pushed at right angles, then I get pushed in a specific shaped path. And what is that shape? Circular motion. So the action of this force in this direction causes the particle to move in a circle. And the name of this force that pushes it towards the centre of the circle is the centripetal force. Okay. So the important part there is all charged particles. Okay. A charged particle, whether it be a proton or a neutron, but for us it's electrons, in the presence of a magnetic field. So the magnetic field causes it, and the magnetic field causes a centripetal force. So electrons get pushed in circles when they are moving in a magnetic field. And that's the basis of making all of our motors work, whether it be a motor in your dishwasher, whether it be a motor in your vacuum cleaner, a motor in our fans up here, any motor that causes motion. Electrical applies where you plug in and you get something to move, that's a motor. Okay. So we'll come to this one here. This is called the right-hand push rule. And we're going to be looking at the FBI rule of motion. But beforehand, before we do that, I'm going to show you a small demonstration of how the motor effect actually causes movement. So we're going to pause here and we'll go and have a look at the demonstration. Now the finger that represents the F is representing force. come on. Nearly got on a pen. Okay, so this represents force, and this is the force that is created by the magnetic field, and it becomes the centripetal force. But it's a force on the wire, so it's a force on the wire. Now B, we haven't come across B much yet. We did a little bit in a preliminary course, but B is the universal letter for the magnetic field. Okay? And I is the universal letter for current. Good. Now, remembering magnetic field flows, if we want to use the word flow, it flows north to south. So the reason why we associate the B field with your index finger is it's going to point from north to south. So the B finger points from north to south. So you're going to point in the direction of the magnetic field. Current. Reminding ourselves that current is also the direction of flow of positive charge. This is conventional current. We know that there are two different versions of flow. One is the flow of electrons, which is the true current, but we can't work with that. It is all designed on proper current, and current is the direction of positive charge. So it's from positive towards the negative. Okay? And the most important part is these three fingers have to be at right angles to each other. In other words, they form a universal right angled plane. Okay? Or what I like to call a pistol grip. So let's just practice getting our fingers in a pistol. So when you play guns, cowboys and Indians, you would use your index finger and your thumb, and the thumb is part of the thing, and your other finger is your trigger finger, and that points out. So practice those three fingers, and it must be with your right hand at right angles to each other. Good. Okay. Relax your hand and form the three finger fist. Okay. Now, this is the second question on your in your book. We're going to have a look at how the electron or the proton or whatever charged particle gets pushed. So on your book there, you've got on the diagram, indicate the path of a positively charged particle. And just use different colours. I've suggested red and blue and green in there. You can use whatever you want, just cross out the colour. But let's have a look, firstly. Now, concentrate with the way I'm going to do this before you copy it. Now, a positive particle enters the magnetic field. Out here, the positive particle, now what is, the proper name of positive particle is a proton, isn't it? Outside of the magnetic field, does it experience any force? No. It simply is going to travel in a straight line. If it's moving that way, it will keep on moving that direction. Once it enters this here, which is a magnetic field, and we mentioned this or discovered this last year, what are these X's trying to indicate? Right, that this magnetic field is into the page. These are the back ends of arrows. If it was coming out of the page, we would see dots, wouldn't we? Okay. So the thing that I just want to rub those out so we get some. What we really need to realise is that if a positive charge is moving in this direction, in that way there, so just change it back, and the direction of positive charge is called current, then current is moving in that direction. So that direction is current. Okay. Now it has entered the magnetic field. And we're now going to work out which way it's going to be pushed. Now we know from the principle we just did a few moments ago that there will be a force on this particle, and it's going to act always at right angles to its motion. And as it acts at right angles to its motion, it will move in what shape? Circle. So it's going to start being pushed into a circle. It has two options. It will be pushed in a circle or a circular path that direction. That is option number 1. Option number 2 is that it will be pushed in that direction as part of a circle. Doesn't have to be, depends on the strength of the magnetic field. I can make it go into a tighter circle or even a more arcing circle, but much less circle. Okay? But we're just trying to work out which direction it will go in what shape. Okay? So let's work out with our FBI rule. So firstly, we want to know which direction is the force. So we're going to use our index finger to point into the board because those X's say it's going into the board. You're going to use your thumb to point in the direction of current. Now current is going that direction, so we'll point our thumb in that direction. So you have that one, and now we extend our Fing finger. And which way is our F? We are F'd up, aren't we? Okay? So if our F is going up, which of the two paths will it be? Path 1 or path 2?
1.
Right. So this would be the shape of a positive particle. Okay? So that's the first one. The second path that you were asked is, what would be the path of a negatively charged particle? We're going to do this in red. Now, if the negative particle is moving in this direction here and it's negative, is that direction current? No. The direction of a negative particle is not current. Current flows in the opposite direction of electron flow, isn't it? So if a negative particle moves this direction, in that way there, which direction will current be? Current goes that way. So in a few more moments, everything's going to be the same, excepting that our thumb is going to point in the other direction. Because if this is a negative particle, an electron for instance, then current is in the opposite direction. So let's point into the board. We point into the board with our index finger, which is our B finger. Our current is in that direction towards the, whatever side that is, left. And now we extend our Fing finger, and we are going to go down F buddies. Okay? Down. Okay. Right here. That sounded terrible that time. Okay. Are we okay with that? So, I was trying to be hip for game stuff. I'm trying too hard. Okay. So, the first one was not bad. It's not just yes. It's going to be on YouTube very soon. And the last one is if it has no charge. Now, going back to the principle of the motor effect, a charged particle in the presence of a magnetic field experiences a force. Okay? So what does a non-charged particle in the presence of a magnetic field experience? No force. Good, excellent. So it goes straight through, unimpeded. And that's neutral. Okay? Okay?
No.
So, we have to memorize this as the principle of the motor effect. So when using it, you quote this phrase. And it's just supposed to be able to be spoken off the top of your head. So the definition of the motor effect is a current carrying conductor. So different from the one before, we were talking about particles. Now we're talking about a piece of wire, because the motor effect is not on single particles but entire wires. A conductor in carrying a current, so a current carrying conductor, a CCC, in the presence of a magnetic field, experiences a force.
Is that the motor effect?
This is the motor effect, yes. So you can copy that directly into part 3 there, question 3. A current carrying conductor in the presence of a magnetic field experiences a force. So let's make sure that we have the letters. Current carrying conductor is I. Okay. In the presence of a magnetic field called B, and we call this force the motor effect. The force on a wire is the motor effect. That's the first part of the definition. The second part is often you don't need to quote it, but for higher levels of answering you might. The direction of this force is at right angles to both the direction of current and the direction of the magnetic field. The direction of this force is at right angles to both the direction of current and the direction of the magnetic field. And can't see the sine theta there. And we get a formula out for it, but the motor effect, because from that definition, would equal BIL sine theta. We now know what B is. B is the magnetic field. I is the current. And L is the only U bit. L is the length of the current in the, length of the wire in the magnetic field. It's the length of the wire, right down here. Wire. So that's what L stands for. And the last one there is sine theta, and we'll get on to that in more in the next lesson. But this is the angle that the wire makes. Okay? And we will really look at this formula in great depth in the next lesson, but not today. Okay?